Okay, dear students, after knowing the different factors, which are symmetry elements, asymmetric, dissymmetric, molecular asymmetry, and molecular dissymmetry, about the stereochemistry. So, we used to study the three-dimensional arrangement of the molecules. As you know very well, when you take a saturated molecule of carbon, which is tetrahedral in structure, all the four different atoms or groups which are same or different will not be in the same plane. For that, when we are writing the molecule on the plane of the paper or on the plane of the board, we have two different types of representations: wedge representation and Fisher representation. So let me take the one by one in detail. Wedge representation. When we write the four different bonds for any carbon atom of a molecule, let me take this is what one particular molecule, and nothing but your lactic acid. This lactic acid is having three carbon atoms, out of which one is the chiral carbon atom. So by knowing the number of chiral carbon atoms for any molecule, we are able to decide the number of possible isomers. For example, lactic acid, though it has three carbon atoms, it has only one chiral carbon atom. According to Van 't Hoff rule, the number of possible isomers for a given molecule is given by a simple relation 2 to the power of n, where n is the number of chiral carbon atoms. For your lactic acid, there is only one chiral carbon atom. Therefore, the value of n is 1. So 2 to the power of 1, that is equal to 2. So that for a given molecule, 2 isomers are possible. Remember, out of 2 isomers, one is on the plane of the board. When you write any molecule, either on the plane of the board or on the plane of the paper, we need to consider like this. Out of 4 bonds, 2 bonds which are written in the normal manner, they are on the plane of the board. Whereas the bond which is having a wedge shape is towards the observer, whereas the bond which is written in the dotted manner is away from the observer. I mean to say, the normal bonds are on the plane of the board, whereas the remaining 2 which are written in the form of wedge and dotted, they are not on the plane of the board. Coming to, when you take the mirror image of the same molecule like this, remember that becomes something like this. So the wedge, the one which is in the left, that will be turned towards the right, and remember, turns towards right. Whereas CH3, it goes towards that is left. Whereas hydrogen, so that will be shifted to right, and that COOH is as it is. In this case, remember, these two are the mirror images, which are nothing but your relations. So, out of 4 bonds, the 2 bonds which are written in a normal manner are on the plane of the board. We need to consider like this. Whereas the other 2, they are not on the plane of the board. They are either projected. The one will be projecting towards the observer, whereas the other one is projecting away from the observer. The one which is projecting away from the observer is written in a dotted manner. The one which is projecting towards the observer is written in the wedge form, which is called wedge representation. Coming to the Fisher representation. In case of Fisher representation, we are going to represent the molecule by writing the horizontal and vertical bonds. And remember, so in Fisher representation, the 2 atoms or groups which are on the horizontal bond, which are on the horizontal bond. So there are 2, we are going to write the 2 bonds. One is the horizontal bond and the other one is the vertical bond. In that horizontal and vertical bond, what we need to consider is the point of intersection of these 2 bonds represents the chiral carbon atom. Please don't forget. So the point at which the 2 bonds intersects, that represents the chiral carbon atom, and the horizontal line, these 2, they are towards the observer, whereas the vertical line is these 2 are away from the observer. I mean to say, this horizontal bond which is having hydrogen and OH group, they are towards the observer, whereas the vertical line which is having CH3 and COOH, they are away from the observer. And in Fischer representation, when you rotate the molecule through 180 degree, remember we will get exactly opposite structure or opposite orientation. Remember, Fischer representation, when you rotate the molecule through 180 degree, we will get the exactly opposite observance of the molecule. That is, OH which was right, that will be shifted to left, H which was right, that is shifted to right, and COOH which is at the top, that is shifted to bottom, whereas CH3 which is at the bottom, that is shifted to top. I mean to say, 180 degree rotation of the Fischer representation will always give a molecule in the opposite observation. So, coming to racemic mixture, as you are all aware, enantiomers are the optical isomers, but they rotate the plane polarized light in the opposite direction. So, when any such two compounds which are capable of rotating the plane polarized light with equal angle but in opposite direction, when they mix in equimolar quantities, that mixture is called racemic mixture. So, a racemic mixture is a very simple mixture which consists of equimolar quantities of both plus and minus isomers. Because of both plus and minus isomers, which since they are present in equimolar quantities, the rotation caused by dextroisomer is cancelled by the rotation caused by the levoisomer. Since the rotation caused by one isomer is compensated by the another isomer, racemic mixture is optically inactive. The optical inactivity of racemic mixture is because of external compensation. I mean to say, whatever the rotation caused by dextroisomer is compensated by the another levoisomer. Hence, the racemic mixture is optically inactive due to external compensation. Okay, I hope you know very well and you might have understood the racemic mixture and its definition and the cause for its optical inactivity. Let me stop at this stage.